So hi, my name is Artur Bujak, and here is my colleague Dominik Rusiecki. We are working in data science team in Ringier Axel Springer Polska, which is one of the leading media groups in Poland. So the most famous brand in our group's portfolio is onet.pl, especially Onet homepage. And in Onet, we believe that if we recommend our users articles which are in line with their interests, we maximize our profits because they will read more of articles. So let's talk about our users. Our users visit Onet homepage to satisfy their needs for information. And there are over 11 million of real users per month. So by real users, I mean that the real people, not the cookies or devices. So it's easy to imagine that in such a big population, the user interest differs. So we can divide our users into groups with similar interest. And that implies the fact that we have to prepare as many versions of Onet homepage, as many groups we distinguished. So we can define this problem as following. We have a content pool, which is a set of articles, and we have to prepare recommendation. So it means that we have to select a subset of articles from our content pool. And more about strategies, how to maximize our performance by selecting articles, will tell you Dominik.
Yeah, so can you hear me? Okay, so when it comes to the strategy, as you probably imagine, there are many different approaches we can adopt here. And some of the more obvious ones probably already come into your mind. Like, for instance, why don't we look at the user's interest based on his historical activity and then try to recommend just items that are similar to those. However, this comes with a couple of pretty big problems. The first one is called filter bubble, where basically the user is stuck in this loop of always being recommended articles which are similar to what he has read in the past, and there is no diversity in that. And the second problem is the user cold start problem, where we don't really have a clear strategy for new users since we don't have a history for them. So this solution, at least in the most naive implementation, will not satisfy us. So the next pretty obvious solution is to just always recommend the top N best performing articles based on their history. But this also has some disadvantages because in that setting, usually what gets its way to the top are like articles with catchy titles or just materials that have been popular for some time, but everyone has read them and are familiar with them. Whereas what we don't see are, for instance, some new trends that are still rising, maybe some breaking news that we really want to show to the user because they're important, as well as just materials expressing different opinions. So this problem is usually called the majority's tyranny, where is the majority that dictates usually most or all of the content that is visible, whereas on the bottom here we see a lot of unexplored potential. So clearly we need something a bit more sophisticated than that, and this is where the multi-armed bandit problem comes in. And so to understand this multi-armed bandit problem, imagine that you are in a casino with a row of slots machines, and you decide to try to win some money on them. And then please also assume that you can actually win some money using some of these machines, but you don't know which ones these are. So some of them might completely rip you off and waste your time and money, while others could potentially make you rich. And furthermore, assume that you only have a specific number of trials during a given time step. So for instance, for today, you might only play 25, you might perform only 25 trials. So what would you do in such a scenario? Well, if you're like me, you will probably start with something very naive, like trying each of the machines just once and seeing what comes out. So let's say this is the result that we get. And surely our uncertainty about these articles has decreased a little bit, but I think you'll agree that this is way too little information to really start acting in a confident manner. So let's say we continue like that. We try to be really fair. So we split all the trials equally, and perhaps we get something like that. So now our uncertainty has turned into somewhat of an estimate about how a given machine is performing, which is represented by the smiley faces. And so based on this knowledge that we have accumulated, we can, for instance, decide that for the next time step, we will only focus on the first 3 machines, therefore probably winning more money with our new set of trials. So what I've just given you is a definition of the multi-armed bandit problem, as well as a simple strategy to deal with that problem. So the problem more formally is defined as choosing k items out of n possible items in every time step t, so that our reward is maximized. Whereas the strategy is mainly concerned with the questions of how do we really choose the subset in each time step, and more importantly, how do we, first of all, store, and second, how do we update the estimates for the articles? As you will see, this might be done in a number of different ways. So now coming back to our news recommendation scenario, we can reformulate it as a multi-armed bandit problem. We need to make just a few simple connections. First of all, the slot machines become the articles that we recommend. The player is the recommendation engine. Each time step is the moment where a user enters our webpage and wants to read some articles. The number of trials is basically the number of articles that we can recommend on the web page. And finally, for reward, we have a click or some other kind of engagement on the part of user. And penalty is lack of such engagement. So please also remember one important fact, that when we think of this as a multi-armed bandit problem, we need to remember that the recommendation engine only selects the subset of the articles, whereas the playing on the machine, you could say, is done by the user himself. So now that we have formally defined our problem, we can now focus on some specific solutions to this problem. And this will be in increasing complexity epsilon greedy bandit, UCB bandit, and Thompson sampling. So starting with the simplest one, which is epsilon greedy. To understand it, we can go back to our example with the top n approach, a greedy approach, but then add a little tweak to it, which is that for some of the articles at the top, we swap them with a random selection from the entire list. Specifically, we might choose some article which is at the bottom of or a completely new one. So as you can see, this will answer our problem of exploring new articles when they appear, as well as countering the tyranny of the majority. And more formally, we choose the epsilon value between 0 and 1, usually much closer to 0. And then with probability 1 minus epsilon, we choose the most popular article available. Otherwise, we choose a random article from the entire content pool. So greedy, as I said, it's as you can see, it's quite simple approach, and therefore it comes with a number of disadvantages, which will be shown by 2 scenarios. First, imagine that we have a new article entering the content pool that we want to explore very intensively in the beginning, because we know that it's, for an instance, a very important event that has happened, and we want the user to see it very often. However, our exploration will be limited to epsilon, because that's the value that we have set, and we cannot really go beyond that. And on the other hand, if we have an article that we know is really bad, and maybe we don't even want to show it to the user anymore, we will still be showing it because of the epsilon, precisely. So this epsilon value, which is fixed, causes us to have very little flexibility in our exploration. So how can we make this better? So here comes the next bandit, which is UCB. And the way it works, again, we can start with the top N list, but this time we will give a very huge optimism boost to the new articles. So much so that they will end up, in the beginning at least, they will end up even higher in our ranking than the well-established, well-performing articles. So more formally, our new rank is defined as the sum of performance, which is just the greedy part, the top end part, and optimism, which, like I said, it starts at infinity, but it quickly decreases as we show the article more and more, so that given article has to rely only on its performance. And C is the parameter that will balance the two. So like I said, this might help us with the lack of flexibility in exploration. However, UCB has its own catches. First of all, it's more complex than epsilon greedy. You have multiple implementation that you can use for that. But the biggest drawback is that on the other hand, relative to epsilon greedy, now the exploitation phase might be too strong. And what I mean by that, perhaps I will, it will be illustrated by this example. So imagine we have 3 fresh new articles, which of course start at the top due to the optimism, and then they get distributed in the list based on how they really perform. So imagine that it happens that one of the articles ends up at the very bottom of the list or somewhere on the bottom. So in the case of UCB, this article will not be shown again at all. And in a way, we might say that this is what we wanted, right? We explored the article and we proved that it's not performing well, so why bother? But the problem is that in our scenario of news recommendation, the situation might be more dynamic than that. So we might expect that some of these articles might start performing better, perhaps simply as a matter of time, or because of some other circumstance. So in short, their performance in time is dynamic, and we have to somehow account for that, whereas UCB really doesn't. So you see we have sort of fallen into the opposite extreme relative to epsilon greedy. And so the question is, how can we find a balance between these two? And probably you already are suspecting that Thompson sampling will allow us to find that balance. So the biggest advantage of Thompson sampling, which is the most complex algorithm of the 3, is that it provides us with much better and complete estimates for the articles. So whereas with the other bandits, all we had was just a single number representing, for instance, the probability that a given article will be clicked. Now with Thompson sampling, we have a whole distribution function for each and every article. And the cool thing about this function is that it can be updated based on how the article is really performing. So we can see that we start with a completely uniform distribution, which represents our maximum uncertainty about this article, so we know nothing about it. And then based on the trials that we perform, we might update this function so that it starts, for instance, in a case of a well-performing article, it starts skewing to the right. And then we can even update it more so that, as you see, the peak becomes narrower, which represents our increasing confidence in this article's performing well. And on the other hand, we can do a symmetric operation where we skew the distribution to the left. And this represents our belief that this article will not perform well. And how do we choose the articles in each time step? We simply have to sample each of the articles' distribution. So we obtain some samples, then we sort them, and just select the top K articles. So more formally, we take advantage here of the Bayes theorem, which, among other things, allows us to estimate the posterior probability based on prior probability and observation, which is quickly illustrated this way. And in our case, we use beta prior, which is really handy because it has two parameters, A and B, that can be used to directly influence the way in which the function will be skewed. So as I said, this algorithm is the most complex of the three, and some statistical knowledge is certainly required to understand and effectively use it. And also the implementation from the technical side might be, well, certainly it's more demanding than the other two. So summarizing bandits as a whole, I hope you've seen that they can really help us with the problems we had, namely that the problem of new articles, majority's tyranny, and filter bubble. And depending on the variant, it can be quite easy to implement them. Whereas the drawbacks, first of all, you've seen that in every case we had some parameters that need to be tuned, be it epsilon, C for the optimism, or the prior function for Thompson sampling. We also need some amount of traffic for the bandits to work decently, simply because of their statistical nature. And lastly, we can't really use the bandit to recommend articles on a single user level. So we have to work on a level of a group or a segment of users, because otherwise the feedback would be too sparse.
Okay, thanks. As Dominik mentioned, articles, the news recommendation problem is a dynamic one. So to understand why it's dynamic, we need to understand that every article has its own life cycle. So there are the kind of articles like news or gossips, which popularity increasing and reach the peak of their performance just after they are published, and after that their popularity is decreasing in time. In the other words, who wanna read about yesterday's weather. And also there are articles like which performance is more stable in time, and the example of that article can be a history article, because you know the history doesn't change as the weather does. Also we have articles which are getting popular only seasonally, like article about how to avoid the bad effects of air pollution in winter. Okay, and to address this problem of changing trends of articles by multi-arm bandit algorithm, we can just adjust our stat window, because we know that multi-arm bandit algorithm makes its decision which articles to select based on stats which it accumulated in previous trials. So to catch the changing trends in article popularity, we can just use only a piece of stats which are most actual. Also, we know, and Dominik show us 3 different types of algorithm, and we know that each type needs to tune a parameter which balance the exploitation and exploration. For epsilon, greedy is of course epsilon. For UCB is a C parameter, and for Thompson sampling, it's priors. Also, we can tune the stats window length, and only in this example we have a 40 configuration. So it's another problem, that how to choose the best configuration for our algorithm in the most optimal way. Because you know the methods, popular methods like A/B testing, aren't efficient enough. So we decided to build a simulator, And in this environment, we can simulate how our algorithm with particular configuration will work. So to explain you a concept of this simulator, let's start what happens in a single trial. So we know that we have a content pool, and we know that we have an algorithm. And that algorithm just selecting a subset of articles from the content pool, and its decision is based on stats which was accumulated in the previous trials. So algorithm prepare the offer, which is a subset of articles from content pool based on knowledge and estimated performance. Also, we know that articles have their own life cycle, and we can generate the data of life cycle, which represents the dead life cycle, in this way that it also represents the user interaction. And we can just compare our offer, and we can see what results we got. So this important part of this simulation is that our algorithm doesn't see the life cycle data. It's just to get our results. So we, in this way, we get stats of the this trial, and we know which article get what performance, and also we got a total payout of this offer. So we know that algorithm in this trial get some reward. And after we repeat many trials, we can say how well our algorithm with particular configuration perform in general. So we can, this is a single run of simulation, and we can repeat that for as many algorithms, as many we want, as many configuration we want to test. And after that, we can choose the best one, which maximized our profit. So if you're interested how our approach is working in real world, you can just visit our onet.pl homepage, because it's fully published with usage of this approach. So if you wanna know more about our approach to recommendation system, to personalization, you can also read our paper, and there are a lot of more details, and there are presented in a lot more formal way. Also, if you have any questions, you can just ask us. And the last thing, I hope that after this talk, when somebody asks you what's your favorite bandit, you don't say it, Robin Hood or Jack Sparrow. You just say multi-armed bandit. Thank you.
Thank you very much. Any questions? Okay. Okay, I try.
Thank you for the presentation. I have maybe two questions. First of all, which of the algorithm is implemented, and what's the influence on the loading time of the page?
So we have actually tried all three of these algorithms. So the way we worked was basically that first we ran the simulations, and then we conducted A/B tests on the selected configurations. And if they proved to be better, which they did, then we deployed them on the whole of traffic. But right now we are only using Thomson sampling, because we've seen that it's the best one. And as to the loading time, it doesn't really matter. Because of the way our recommendation system is built, there's no difference. Yeah. Yeah, if there is a difference, I think it's very, very small. So.
My question, are you still able to manually select the articles? So for instance, you have like sponsored article, which you want to put on the main carousel banner, for instance, for one day. Are you still able to manipulate that?
Yeah, so the recommendation system that we use has the ability of pinning, which is basically that you can specify, okay, put this article on the second position and keep it there, whereas all the other positions are managed by the bandit. So.
Are there any challenges left for you when it comes to the main page, or you're pretty satisfied with the current Thompson sampling recommendation?
Well, there are some challenges. I'm not sure how much we can disclose regarding that, but
you know, there is always a fight to optimize and make our system better. So, but the results are pretty great. So it's working now. It's working fine, and so that's the next steps. Okay, so thank you again.